Oh, welcome to the video. Uh, in this lesson, we're looking at section 4.8 where we're going to be analyzing graphs of polynomial functions. One of the questions that we are going to be asking is how many turning points can the graph of a polynomial have? So here is essentially what I'm asking you to do in order to graph these functions. Okay, so again, if you have a graphing calculator, it'll certainly help you out, but these are the things that I'm looking for, and I specifically want you to label. First thing I want you to look at, and we talked about it at the beginning of this chapter, is be able to describe the end behavior. All right, so that's the first thing. Be able to describe the end behavior. So basically you're looking for is your lead degree odd or even? Is your lead coefficient positive or negative? Whatever that may be, I would certainly reference those notes to help you out and then kind of go from there. Second thing I want to be able to find is the y-intercept. And the y-intercept for any of these functions is going to be 0, comma, whatever the constant value is, whatever value that has no variable attached to it. If there is no term with no variable attached to it, it's going to be 0. So keep that in mind. Next is I want you to find the x-intercepts. And then the final thing, and which kind of answers the essential question for this lesson, is how many turning points? So in order to look at a turning point, let's look at one of these concepts. Turning point is basically means this. So figure out what the degree of this function is. Whatever that degree is, you're going to have at most n minus 1. So if you have a third degree polynomial, you're going to have at most 2 turning points. And if you notice that you have all real zeros, you will have exactly n minus 1 turning points. So, with that being said, let's look at being able to graph this particular function. So, it says f of x equals 1/6 times it by the quantity of x plus 3 times it by the quantity of x minus 2 quantity squared. So, I look at this, and the first thing that I would do is let's multiply it out and get it as a polynomial that you would type it in your graph or graphing calculator. So this is just going to be 1/6 times it by x plus 3. I'm going to expand this as x minus 2 times it by the quantity of x minus 2. This, again, is the pattern, so I'm just going to write this as 1/6 times it by x plus 3 times it by x squared minus 4x plus 4. So leaving the 1/6 out still, this is now going to be x cubed minus 4x squared plus 4. That was just me multiplying these together. Now with the 3, it's going to be plus 3x squared minus 12x plus 12. And now I have, what, 1/6 times it by the quantity of x cubed. Square is there, so it's going to be what, minus x squared. And then cross that out. Well, we got minus 12x. This is x, so this would actually be minus 8x plus 12. And multiply everything by the 1/6. So I got what? 1/6 x cubed minus 1/6 x squared minus, what would be what? 4/3 x plus 2. So I got the constant value of 2, so that means that my y-intercept is 2. So got that. Describing the end behavior, I can say now, right now, um, my degree is odd, my lead coefficient is positive, so that means when x is going negative infinity, so is f of x, so your graph is going to start somewhere down here, and it's going to end somewhere up here. All right, now looking at the x-intercepts, it comes from here. That means that my x-intercepts would be what, negative 3 comma 0 right here, and positive 2 comma 0. Now remember, because you have this square of a binomial, this is a repeated solution, which means it's just going to touch that intersection, and then that's also going to be a turning point. So because it is x to the third power, my guess, well, there's how many turning points? There's only going to be 2. So here is kind of what I believe this graph is going to look like. So it's going to start down here, it's going to cross here, and then it's just going to touch right there, and it's going to come here. This is turning point 1, this is turning point 2, and this is how the graph is going to look like. So just to give you an idea, let's see how close I was. Let's type this in. So if I said 1/6, and then it's going to be x plus 3, and then we got x minus 2 quantity squared. I'd say we were pretty close. Okay. And again, you don't need the graphing calculator to do these per se. It's just you know, a way for you to kind of double check what these different functions are looking at. So kind of the same idea. Looking at, let's say like this one here. Looks like we have another one that looks like it's just touching. So let's multiply it out. So we got 1/2. We got x plus 1. This one here, if we expand it out, it's going to be what, x squared minus 8x plus 16. Multiply the x plus 1 with the x squared minus 8x plus 16. So I got the 1/2. And then this is going to be what, x to the third. And we got what, minus 8x squared. We got plus 16x. That one's done with the 1. It's just going to be plus x squared minus 8x plus 16. With the 1/2, I got 1/2 x to the third minus 4x squared. Oh, shoot. I forgot to combine like terms. So x cubed, that's there. X squared, so it's minus 7x squared. Here and here we got plus 8x plus 16. Now we take the 1/2, so now it's 1/2 x cubed minus 7/2 x squared plus 4x plus 8. So constant value is 8. That means that 8 is my y-intercept. It's 8. My x-intercepts are going to fall on -1 from here and +4. 1, 2, 3, 4. And remember, because it's that quantity squared, that's where my turning point is also going to be. This is a similar situation where with the end behavior, my lead degree is odd, my lead coefficient is positive, which means it's going to start here and over there. So let's see if I could make a guess. I would say it's going to look something like this, this, and this. And because it's 3, that means I'm going to have 2 turning points. And you're more welcome to check it with your graphing calculator, see how close it was. You can double check to see how close I was. All right, and then here it's asking how many, it says all real zeros. So it doesn't matter about the imaginary one, it just wants the real ones. So it's 4 terms. My advice is let's use the graphing calculator to give us an approximation. Hopefully there's some integers that we can look at and then implement synthetic division to prove that those are in fact solutions, or those are in fact zeros of the function. All right. Looks like we got -2. So let's put -2 in there. So I got 3, 2, 1 constant. We're good. So 6, 5, -17, -6. So let's see how close we are. So we got 6, -12. We got -7. We got 14. We got -3, +6, 0. Great. -2 is in fact a solution. Now from here, it looks like I could write this as the function of 6x squared minus 7x minus 3. Now, right off the bat, I do not know if these particular values are going to be factorable, but let's give it a try. So I know that 3 is a prime number, so I'm just going to write 3 and 1. I know that the products of 6 are 2 and 3 and 6 and 1. All I know is that the difference of these two values plus the difference of these two values have to give me a -7. So if I put, let's say I put, if I put 2, let's say I put 6 here and say I put 1. No, that won't work. Let's say I put 3 here and 2 here. 2 times 1 is 2. 3 times 3 is 9. That's where the difference is 7. All right, cool. -7, which means that the negative has to go with the 9. Positive has to go with the 2. So this is 2x. This is 3x. That means this is the minus. This is the plus. So that's nice. So final step here is taking 2x minus 3 set equal to 0, 3x plus 1 set equal to 0. The real solution here is x equals positive 3 halves. Over here is x equals -1/3. I have 1, 2, 3 solutions, third degree. So I found our real solutions or all real zeros. This one here, again, I recommend you do using the same methods that I did, checking the graph, using synthetic division, and then proving it from there. If you can factor it and go from there, those are other methods as well. If you have questions, please comment down below. Again, more than happy to help you out. And that is being able to analyze graphs of polynomial functions. I hope this helps. Until next time.